So we were talking about e yesterday, and we know that e is like pi. It's a special number. It's 2.718, and then you can keep going, right? On our calculators, if I'm taking a look at my graphing calculator, there's two places where you can find the e. One of the places that we saw yesterday is right above the division key. There's a little lowercase e. There's also one over on the far left underneath the log button. You see it says log, and then underneath that there's an e to the x. So there's two places that we can get e on our calculator. If you hit the second button and then hit e to the x, or the ln button, you'll see it'll put an e, well, I guess you can't see that very well, but e, and then there's a little exponent thing flickering there. If you put a 1 there, e to the first, and hit enter, you get what e is. Or you could also hit second and then the division key and get e that way. Okay. So it's a special number like pi, and it happens whenever we have continuous growth. So it's used for continuous growth. So this word continuous is going to be something you're going to be looking for today as a clue of when you're supposed to use a formula with e in it, or when you're supposed to use the formula that we've been using. The formula with e in it is a equals p times e to the rt, and these rt up here is up in the exponent, it's up in the power. The formula we've been using is very, very similar to this. So the p, what's the p stand for normally for us? Our p is what? It's our starting value. It's our initial amount. And then e is Euler's number. The r is the rate, the interest rate, or the growth rate. And t is time. And it's usually in years. It's usually measured in years for these formulas. So an example of somewhere that you might see a formula involving e or a problem involving e would be with like population growth. So let's say a city's population is 1,500 people in 2013. If it grows by 3% per year, how many people will there be in 2020? Huh? Say what? Yeah, so this is sneaky. With things that happen in nature, like population growth, bacteria growth, nature doesn't really follow a human timeline. It's like if we were talking about when babies are born at the same time every day, once a day, every day. Right? Not born on a monthly time frame, like, oh, once a month, okay, here comes some babies, right? Yeah, it'd be crazy, right? You wouldn't have enough doctors. So because things happen continuously, these are born continuously throughout the day. Like every second of every day, somewhere in the world, a baby is born. And it's not following this like regimented, like once a month time frame that we've been looking at for like financial stuff. And so even though it doesn't say the word continuously here, if you're talking about population growth, it's implied that it's continuous. So we're going to use the PERT formula right here. So we would say A equals our principal amount, which in this case would be 1,500, and then times Euler's number times E. Now, I'm going to write up caret here to remind myself that this is up in the exponent. And then we want both of the r and the t to be up in the exponent. And so if you're going to plug this into your calculator, you're going to have to put parentheses around it to group it together to tell your calculator that, hey, I want all of this up in the exponent. Now, 3% interest is what as a decimal? Good. It's 0.03. And if you couldn't remember what it is, what's the trick? What do you divide 3 by that'll give you 0.03? Good. You can divide it by 100. So this would be 0.03. And now from 2013 to 2020? 7 years. So this would be times 7. Okay. So then it's really nice on this formula, since your calculator knows order of operations, you can just literally plug it in exactly like you see it. So 1500 E, so you're going to hit second and then the LN button to get your E. And then parentheses 0.03 times 7. And we get about 1850. Now with people, can you have 0.5 of a person? It's like half of a baby's been born. Yeah. Yeah, right? So should we round this up and count that half of a baby as 51, or should we cut it off and not count the baby and leave it at 50? Huh? So it's 1850.5. Up. I would round it up. So we're saying about, we're going to use squiggly equal signs to say approximately 1,850. Oh, and then I'm going to round it up to 1 people. Yeah, it's kind of hard to determine where's that half the time period. We'll just round it up. All right, so the only other example we're doing, guys, this is our last example, and then I'm going to let you guys go on your homework. So you invest $1,000 into an account. You plan on leaving it there. So in this situation, you've got $1,000 to invest, and you're planning on this being like for retirement. So you want to leave it in there for all. You're shopping around interest rates, and you're shopping around at different banks, looking at like where you should invest it. And you have one option, option A. Okay, so investment A gives you 5% interest, but it's compounded quarterly. Option B gives you 4.9% interest, and it's compounded continuously. And so you're trying to figure out, because you want to get the most money that you can, which one of these scenarios is going to be better. So to do this, we're going to have to use our formulas. Now, since we've been talking about PERT and we just have notes on PERT, let's do that first. So we'll do the continuous situation first. If it's counted continuously, if you see that word, you're going to use APERT. So principal amount is how much in this problem? It's 1,000. And then times E times Euler's number. All right, good. What's the R going to be? Good, 0.049. And then what's the time period? 30 years. Good. So go ahead and type that into your calculator once you get it written down. And we get, I'm getting $4,349. Is it 23 cents or 24 cents?
24.
24 cents, good, it's gonna round up. Okay. And then compounded quarterly, we're gonna need to use that formula that we were looking at yesterday and that we've been sort of working with for a while now, right? So just a reminder, that formula was A equals P times 1 plus R over N to the NT power. So our P is the same, it's 1,000. What's our R in this case? It's the rate, it's that 5%. What do I do with the 5%? Oh, I'm eventually going to divide it by 4, good. To plug it in for the R though, what do I need to do to the 5? 0.05, good. Because it's 5%, so I have to change it to decimal. And then up here in the up caret, this is to the 4 times 10 power because it's, oh wait, 30? Yeah, 4 times 30 because it's 30 years. Now remember, on ones like this, even though it looks all complicated and there's a lot of stuff to do, 4 times 30. Because it's 30 years. So on my calculator, I can just plug this in. I showed you guys that yesterday all at once. So you can plug in 1,000 times 1 plus 0.05 divided by 4 to the 4 times 30.
1 billion.
What? 1 billion? I'm getting 4,440.
That's what I got too.
Did you make 0.05? Okay.
No, I got what you got.
So you got a different number? Did you do 0.05?
Yeah.
Did you put parentheses around the 4 times 30?
Oh, no.
That's why.
I'm gonna say the same thing. I do the exact same thing.
Yeah. Okay. So which situation was better for us?
Really?
Do we care more about the 5% interest or do we care more about the compounded continuously? Which one gave us more money? The quarterly, right? The 5% interest, that 5% mattered more than giving us interest continuously, than compounding us continuously. By about $90, right? It's a decent difference.
I'm kind of stupid.
I know. All right. We will go ahead and work on our worksheet now.